Well, thank you very much. My name is Jippe van Ruiten. As I told you, it's very impolite, and I realize that it's, but in order to have a fighting chance to catch my flight, if you want to get in touch, please send me an email and get back to me on this. The content will be twofold, basically. I will give you a short introduction into DSM, what motivates us in the core, show you some relevant recent applications, and then get into the beef of one example of how we interact with the automotive industry to improve fuel economy, the central theme in this whole symposium here. DSM basically is really committed to innovation and sustainability, and to paint you the picture of where our company is going. Perhaps this is the strongest statement that our CEO has made. We cannot be successful, nor can we call ourselves successful, in a society that fails. DSM is really stepping up to its corporate citizen role. For instance, we've been part of the United Nations World Food Programme for over 15 years, an active partner. Employees at DSM can take 1 or 2 months leave and interact with one of the United Nations programs there. We've been in the Dow Jones Sustainability Index for the last 17 years, of which 5 years at #1 position. So our mission is to create better lives for people today and generations to come. What do? Well, we nourish, we protect, and we improve performance. DSM Engineering Plastics is in the performance materials cluster. DSM towards automotive, well, we're a leading global supplier of engineering plastics, of composite resins and coating resins. As said, we have an innovative focus. Our innovations need to focus on sustainability, emission down, fuel down, safety up, comfort up, NVH, those type of topics. And we take pride in knowing the applications in which we want to generate added value with our partners in specific automotive subsegments. So one example where synergy has been found between the enzyme technology at DSM, joint venturing with the US company Poet, where jointly we've come up with a system to produce bioethanol from agricultural waste. So bioethanol not in contact with the food chain. Another example of how our products help facilitate innovations. Here's the low friction camshafts by Mahle, where our stenil material is being used as a bearing cage material to facilitate the assembly at high temperatures of these camshafts. Another example in fuel permeability of fuel tanks as well as compressed natural gas tank liners. What we've developed is a polyamide 6 material with extremely high barrier properties against volatiles passing through. And we have a blow moldable version of this material where CNG tank liners have been molded, which are then wound over with continuous filament carbon fiber to produce lighter CNG tanks. Next to CO2 emissions, fuel economy, NVH is an extremely hot topic in the automotive. And here's an example where our high-performance plastic enable to produce plastic gears that enable the balance shaft drive system, reducing cost, reducing NVH or improving NVH, and reducing weight. A further example is a crankshaft cover where a dynamic seal is overmolded with a plastic tuned to CLTE for the metal engine block, the girdle here, and then in a second shot the liquid silicone gasket is overmolded, ready for assembly at the engine. So that was the first part. The second part basically homes in on how to help the automotive industry improve their fuel economy. And one way is to lower, and now there we go. So one way to, one aspect, one opportunity where we can reduce friction is in the timing system. So if the crankshaft, the camshafts, an oil pump at some points, there are two major contributors to friction in this subsystem, which is the chain articulation, where the chain runs onto and runs off the sprocket. The location of interest right now is the chain guides on the guide and tensioner, where the chain slides on the plastic and generates friction. What we've been looking at on academic tribological test stands is to measure the coefficient of friction as function of temperature, where here you would have the incumbent PA66 high molecular weight plastics, where our Stanil PA46 shows a 20% lower coefficient of friction. Now this can, in a hand-waving way, be understood from the stiffness as function of temperature, where the blue line here is PA66, the green line is PA46, to give you some automotive frame of reference. Oil sump temperatures typically at 90 degrees, a friction interface temperature roughly at 140, max in 66. At those local stiffnesses, Stanil PA46 is able to give you the same local stiffness at the chain-to-guide interface at easily double the overheating of the chain, which basically explains why nylon 46 is being recognized by the industry as the most robust material in this application. Back to friction reduction. We're collaborating with all tier ones globally in timing systems. This is just an example of our collaboration with BorgWarner, who on their chain-to-guide friction test rigs have confirmed the 20-25% benefit of coefficient of friction now measured against normal temperature. So again, this confirms the benefit of PA46. A further collaboration was with Ford Motor Company, where Ford took their 2.4 Duratorque diesel engine and exchanged these chain guides and fixed guides from PA66 to PA46, put the engine on a motored friction test rig, rotate the engine with an electric motor, and measure the torque needed to overcome friction. The difference for this fairly complete engine between an engine fitted with PA66 in blue versus PA46 in green roughly is 0.45 Newton meters less friction torque across the whole RPM range. Now at DSM, we took the challenge to see, okay, can we explain this 0.45 Newton meters benefit measured on the engine from a 20% lower coefficient of friction? What we did, and I won't go into the details here, is basically take the engine layout, take the radius of curvature for the 3 different guides, take the contact angle from that, from the chain linear tension. You can calculate the normal force multiplied with the coefficient of friction. You have the sliding friction force times the speed, you have your friction losses. Now this is calculated here. What happens if you lower the coefficient of friction of these 3 contributions? Well, you will lower the friction by something like 100 watts and at 2000 RPM engine speed, this exactly is equivalent to 0.45 Newton meter. So we've been able to confirm and explain how Ford convinced themselves that there was an intrinsic benefit to be had from these plastic materials, and how, using this fairly rough calculational model, how it would transfer to other engine geometries. This was all published together with Ford. If you drop me an email, I can send you a PDF file on this. It wasn't just Ford, also, here's another example by Hyundai Motor Company, who on a mid-gas engine did similar experiments, measuring a difference between PA66 and 4.6 now, because the engine is simpler, of 0.2 Newton meters, again confirming the general benefit to be had. Cost is always a matter and a factor in the automotive industry. Here you see results originating from a survey that McKinsey performed in 2010, published in VDI Nachrichten, German Society of Engineers weekly, where they questioned the automotive industry. Okay, state of art 2007. European fleet average CO2 emission was 159 grams of CO2 per kilometer. And the question was, dear automotive industry, what type of technologies do you need to put into a car, state of art 2007, to reduce the CO2 emission to the level of 95, which is the aim per 2020. And if you add these type of technologies, what is the cost per car that are involved in applying this? Well, in sake of time, let's focus on the most cost-effective technologies that we have at hand here. So they would include mild weight reduction, low rolling resistance tires, variable valve timing, and indeed mild friction reduction. These technologies would typically have the capability to lower CO2 emission by 19 grams CO2 per kilometer, and they would come typically at the cost of 13 euros per gram of CO2 less. If you go back to the example at the Ford engine, you don't need a whole lot of plastic to exchange the chain contact parts in the timing system. So yes, indeed, the PA4.6 comes at a higher cost. It will generate a cost increase of roughly half a euro, say, per engine. The benefit, a conservative estimate, would be around 1 gram of CO2. So you would be at half a euro per gram of CO2 compared to the most cost-effective 13 euros per gram of competing technologies. So by all means, this is supporting our claim that exchanging this plastic is the most cost-effective way to improve fuel economy. Conclusions. Well, on the friction reduction end, we can go through it again. It's basically the most cost-effective way. It doesn't really need reapproval because the PA4.6 is recognized as the most robust solution material in this industry. Meanwhile, a whole set of OEMs have convinced themselves on their own test stands. And I'm showing you this not per se to kind of convince you of these great materials, but as an example of how we interact with the industry, living up to our motto, bright science, brighter living. Thank you very much.